welcome to this electron atomic physics. I'm going to start off a little bit different from most people what they would. I'm primarily focusing on the Schrödinger equation for the hydrogen atom, because this is a concept which people seem to struggle with the most, especially when it comes to deriving the polynomials for the spherical harmonics and the radial equation. But a quick note to begin with is that like when it comes to mathematical physics, most equations cannot be solved analytically unless it's a strong approximation to the standard shapes in geometry like given above. But these can easily be extended to higher dimensions, such as cubes, spheres, and if you know anything about fluid mechanics, you would understand the idea of a sort of fluid parcel, which is thought of as like a part of the fluid in continuum mechanics that moves along with the fluid, with the flow. Well, it's thinking of physical phenomena in terms of these shapes from pure mathematics allows us to come to the most accurate solutions. Well, anyway, let's begin with looking at the Laplacian, the spherical Laplacian, which is here, which you would have seen before, I'm assuming, if you're watching this. First, we'll take this spherical Laplacian to equal 0. Assume we have azimuthal symmetry, and we separate this into its radial and theta components, and we plug in and divide by this radial and theta, and then multiply by r squared, which will give us this form here. And the first term depends only on r and on theta, so each must be equal to choosing a constant. And in this case, this will be the constant, the one that practically everybody uses for I'm guessing that mathematicians probably derived that this was the best possible constant you could have for this type of equation. But anyway, moving on. And for the radial here, we obtain the L plus 1 solution to this radial component here, and this is the theta component here with the L plus 1 equals 0. So the radial above, which is often written in this form, and the angular equation here, we now show the angular equation is Legendre's equation, where x equals cosine theta and theta equals y of x. And using the chain rule here, we obtain y prime of x and minus sine theta equals minus sine theta and y prime. And sine theta, d theta by d theta, large theta, equals minus sine squared theta, y prime, there should be a prime there, and which equals minus 1 minus x squared y prime. And we differentiate theta once more, which gives us here, and we use a chain rule, which gives us minus sine theta d by dx. So d by d theta sine theta theta prime equals minus sine theta d by dx minus 1 minus x squared y prime. So plugging into the angular ODE, we will obtain this d by dx 1 minus x squared y prime plus L plus 1 y equals 0. And expanding it into a standard Legendre form, we get this here, which should become a little more familiar. And this is Legendre's equation of degree L. And regularity at its endpoints, theta equals 0 and theta equals pi, force L to be a non-negative integer, in which case solutions y of x are Legendre polynomials PL of x. If azimuthal symmetry is not assumed, but as separate phi dependence as I to the m phi, the angular equation becomes the associated Legendre equation here. where m is contained in the integers. The magnitude of m is less than or equal to L. Here. And that's the mathematical derivation.